Awesome. So today I'm going to talk about when your processes or your systems that you have bad neighbors, and specifically how this can happen in hardware environments. So just to start off, who am I? I'm Sophia Antoine. I work as a security researcher in New York at Trail of Bits. And most of this work that I'm presenting is built off of the work I put into my master's thesis, which I finished last year. And in my free time, of course, I play CTF, so feel free to talk about that with me afterwards. So this is the overview for the talk today, and I'm just going to start off with a general introduction to what side channel attacks are, though I'm sure a lot of you have a good understanding of that. But specifically, when we talk about attacks in the world of side channels, what we actually mean is information leakage. So not necessarily an attack of what I call the first order, right? So like memory corruption, something where you go in and alter the target itself. Side channel attacks are generally attacks which do not alter or change the program that you're targeting, but change the system that that target is interacting with, or they win based off of information they can gain from the system that that target is interacting with. So specifically, an attacker, when looking to form a side channel attack, observes the target system, but cannot introspect into it. So he must have a few things he can do. He must be able to repeatedly query the system that that target is operating in, as well as know that what he's querying isn't altered by his introspection into it. And that's the building blocks for a side channel attack. There's different types of side channel attacks, specifically in the realm of hardware. So common ones are the ones I've listed here, like fault attacks. And that requires access to the hardware. So you're flipping bits by changing the heat that a specific part of the hardware has, or something like that. Power analysis side channels are when you take readings of the system and heat signatures and how that interacts with the environment to gain information about what the system is doing. And then the last one is actually the most common. So a lot of side channel attacks that are coming out in the past few years have really used the element of time and timing attacks to gain information about a system or do some other sort of attack with it. And this requires process co-location. So that means that your attacking process has to be co-located on the same hardware to perform that timing attack, or co-located in the same system. So an example of that would be network packet delivery time. So your attacking process would record that packet delivery time, but in order for that to be profitable, it must be co-located or neighboring of the target attack. The targeting must be co-located with the target. So it must be on the same machine or on the same network as the target that you're looking at. So this is just an example in cryptography. Usually in the realm of academia and research papers, to prove you have a hardware side channel, they usually apply it to cryptographic functions and breaking crypto, so leaking private keys. And once you can do that, you have a good side channel. And so in this case, this quote's from Wikipedia, but you're observing an RSA key encryption using the private key. And using power analysis, they can form this graph here. And a lot of it ends up becoming, taking lots of readings over time of the power that that system is emitting during this encryption using the RSA private key. And taking those measurements over time, you can look at it and start to see patterns forming. And most side channel attacks end up becoming pattern recognition. So you take lots of data points, you keep making measurements or keep doing something repeatedly until you can extract out meaning from that system. And so here you see that taking lots of power readings and sampling power from that system, they were able to say that for the majority of the time when the power sampled in a specific time frame is over a certain threshold, that can be represented as a 1-bit, and so forth, until you have the whole key. And this is just a depiction of what's going on here. So what we're doing is we're gaining information through measuring recordable changes in the system. So in this case, it's the heat signature of the hardware itself, so the implementation of the crypto system. And we treat that implementation of the crypto system as a black box, but we're making those measurements of recordable changes, in this case the heat, over a period of time. And that delta will tell us if it's a 1 or a 0-bit. All right, so that was a very specific example, but there's some basic requirements that all side channels have. So power, timing attacks, fault attacks, those sort of things. They all require 3 main primitives, as I call them. And the first is a shared environment. So you have to have some sort of medium that you can both query and know that you reading that system or measuring that system doesn't alter the measurement itself. And the transmitter in this case would be the encryption process. So it's the process that you're targeting. It's running on the system, and because of its behavior, it's changing the system. So it's affecting that shared environment. And from a receiving standpoint, as the malicious attacker, you're reading information from that shared environment put there by the target or the transmitter. But that measurement of the information does not alter the shared hardware. So these are 3 common primitives across all side channel attacks. All right, so using these 3 different kind of structures here, we can actually form 3 different classifications of side channel attacks. And the first scenario is the one I've been talking about kind of up until this point. And that's when your transmitter is unaware that it's transmitting. It's running its encryption processes on a CPU somewhere, and it's unaware that someone's eavesdropping on it. And the receiver is gaining information from that system. So reading some information from that shared hardware that allows it to make some sort of mapping between that gained information and the transmitter's RSA private key. So that's the first application of this, but there's other things you can do with this sort of model of active, unaware transmitting process and a malicious eavesdropper or recording process reading from the system. There's many different research papers that went into environmental keying, so determining co-location on the same hardware, for instance. A broadcast signal, so for instance, if you have a botnet structure and the transmitter is doing some sort of behavior on the CPU or on the shared environment that the receiver can glean from the shared environment, that can be treated as a broadcast signal. So there's many different applications of it, but that's more about intention and not about the vulnerability itself. All right, so the second scenario is actually the opposite, right? So you have a receiver which is recording from the system but is unaware that it's recording. Just basically noisy processes running on the system. The transmitter, however, is intentionally sending specific behavioral patterns to the shared environment. And what actually happens here is you can do something like a DOS attack. So for instance, a process uses up all the CPU time. Let's say the scheduler is really bad and just completely takes over all the shared resources, kind of like mine, and then it means that no other processes can use it. So this is kind of less discussed. It's not as interesting necessarily to researchers in the past few years, but it's definitely another application of a side channel. And the third scenario is when both of them are intentionally sending and receiving to each other. So for instance, you have 2 processes running on a shared environment, and both of them are intentionally sending behavioral patterns to the system and recording them from the system back and forth. And this creates something like a classical covert channel when you read about that. And this communication medium, specifically in this talk, is the shared hardware, but it can be anything, right? So you have the idea of forcing some sort of behavioral pattern and recording that pattern to create a covert channel. All right, so we have this basic model of receiver, transmitter, and shared medium to create a side channel. But what happens when we apply that to hardware? Okay, so we're going to start off with the same model. So we have a transmitter receiver. But now that shared environment or shared medium is hardware. And this kind of changes the state of what we can do slightly. So if you have two processes running on the system, be that in separate operating systems or in one operating system, maybe one process is inside a VM, so it's sandboxed, they all end up sharing actual hardware components listed here. So like the processors, the cache tiers, system buses, they all end up sharing these things. And these would become the medium that we're using to send and receive artifacts for our channel. All right, so in this specific case, we are using CPUs or caches or other aspects of a computer to create a side channel. The transmitting process must be able to do these things. So we talked about this before, but it must be able to affect the state of the hardware component that it's using as the medium. And that must be in such a way that is completely observable and recordable from all other processes, and repeatable. So it can send some sort of message repeatedly over time. But at the same time, it can't do it in such a way that the optimizers on the computer will mess up somehow. It has to be reliable. So that is one difficulty people have with creating side channels over hardware. On the other hand, the receiving process must be able to record these changes in either the pipeline or the cache tiers or the main memory, but do that without affecting the actual artifacts that are being placed there, without affecting the transmitted behavior that the transmitting process is putting there. All right, so we have these primitives, going back over them. We have shared pieces of hardware resources, so we're sharing the same cache or the same pipeline between multiple processes. These resources are dynamically allocated. So on all modern computers, one process isn't allocated X amount of space in the cache, and that's its piece of the cache for the entire run of the process. That's not how computers work because it's not efficient. So all resources that are shared between processes are dynamically allocated based on need. And we can actually abuse that basic optimization that modern computers use to create contentions between processes. And this can take many different forms depending on which hardware unit you're using. But the real vulnerability for all hardware side channels is that element of dynamic translation and forced contention. And you can use that optimization model to deterministically send messages and create covert channels across different pieces of hardware. Yes, like I was saying, it's that physical co-location. So your two processes are running on the same computer. That contention between dynamically allocated resources, and this leads to the actual vulnerability. And this actually happens most frequently with processes that you don't know of, or maybe operating systems that you don't have control of in the cloud. So when you're running two processes on your own computer, there's a good chance that you know what's going on. But in the cloud, you're actually sharing hardware with processes and operating systems that you have no control over. And they might be malicious intentionally or not. right, so how can we create these side channels over hardware in the cloud? So everyone here probably knows the basic structures of cloud computing, but you get a bunch of virtual instances, as seen here, and these are allocated on one large hardware unit, and this allocation happens through the hypervisor. So we've had a couple of talks the past few days on that hypervisor level work and things, but that's the main idea of the cloud. And the reason that's done is because this dynamic allocation between real hardware resources and the virtual hardware resources as seen by the operating systems reduces costs for everyone. So it's a good business model, it works. But this is basically the idea of force contention and resource allocation, but on a very large scale with processes that you haven't created yourself, so foreign processes. All right, so in the cloud, kind of taking a step back, there's a few different attack scenarios, right? So a lot of people may not store their data in the cloud because it's stored remotely. They don't have physical access to that piece of hardware storing their data. The host might be vulnerable or untrustable, but the one we're focusing on is the fact that your processes are co-located with foreign VMs, with foreign processes, and they're sharing that physical hardware down here. And this is just another diagram of how that looks, just showing the virtual allocations, which are created dynamically across time by the hypervisor to basically share that physical resource down here. All right, so creating hardware side channels in the cloud. We know that we need a medium to create a side channel, and in this case, it's going to be one of the hardware units that I listed earlier. We're going to try and do an attack which is cross-VM, so from between two processes, but one process is in one VM, the other is in another. And the method of, I guess, creating a side channel attack here is making recordable changes in the system and enforcing those and receiving those. And that vulnerability, like I talked about before, is the translation between physical and virtual, and the contention that causes. And this is just depictions of the different types of scenarios you could have where perhaps one virtual machine is intentionally malicious, or it's just the process inside of it. Or there's two processes in the same operating system. One is malicious and one is not. So there's many different ways in which these hardware side channels can actually be applicable to your process. All right, so I thought it'd be kind of fun to show how, if you ever want to get a research paper out or do something in your free time, it's actually quite simple to kind of build your own side channel. You only need a few different components, and maybe it'll be more or less effective, but it's very methodical. So the first step is to choose the medium. So what medium are you going to use to send and receive signals across? So you can choose different shared pieces of hardware in this case. The cache, for instance, there was a great talk earlier about that, or the processors or the system buses. So something of this, you have to choose a method that you're going to use to make a measurement across this shared piece of hardware. So are you going to use a timing attack across this shared hardware to measure cache misses and use that to send bits of information? Are you going to use computational results to say, oh, an incorrect value here can imply something else? Resource contention is something else as well that people have used. I've seen a paper where a researcher took two different processes and locked the memory bus on the entire computer, and that was one bit of information. It was a very strong, noiseless side channel, but also very noisy in the sense that it was detectable. So that was funny. But any other way of measuring your piece of shared hardware you can use to create a side channel. All right, so now we're going to choose an attack model. Are we going to choose scenario 1 or 2 or 3? This depends on what sort of attack you want to do. For the sake of this talk, I'm going to go ahead and keep discussing it using a recorder only, so just kind of eavesdropping on other processes on the system, like in the crypto RSA key leak example. All right, so I kind of discussed some different case studies before, the memory bus one. Also, the cache side channels are also quite common. It's not easier to use the cache, but it's more reliable because that hardware medium is static. And what I mean by that is that you can send bits of information or receive them pretty deterministically. Because it is memory, you can say, oh, my value is in memory in the tier 1 cache or the tier 2 or 3. And you can know that it's either there or not, and it's very binary. So it's a very strong side channel medium. All right, so there's some difficulties associated with different mediums that you choose. So is it easy or not to actually query that hardware unit? Like I said before, the cache is pretty deterministic in the sense that you can see if your value is in memory or not at a specific location. But other hardware units are less reliable or more difficult to measure. For instance, using the CPU's pipeline. You actually can't introspect into it, right? Because if you wrote some instructions that introspected into the pipeline, you'd be changing the state of the pipeline itself. So you have to do is come with more roundabout ways to make measurements of harder side channel units. So this diagram is based off a literature survey I did last year, and it's in here more for notes later on if people are interested. But it just kind of outlines popular transmitting and reception mechanisms used in the majority of research papers out there for different side channel mediums. So, for instance, main memory, a very common transmitting mechanism is priming and probing shared memory in the main memory unit. And you're measuring access capabilities. So that could be mapped to specific bits of meaning or something. And this, again, is a similar diagram, except a bit more simplified. So for instance, I'll go over the functional units is quite interesting. So you're transmitting bits of meaning by using a method of resource eviction in the functional unit. And from the receiving process, you can time to see if your threads that you create have the ability to use different functional units on the shared CPU. And that can be also mapped to different bits of meaning. So you see here that timing is quite popular as a form of receiving information. All right, so I'm going to go into some demos, as well as more specific examples to different hardware units. So this first example is kind of an outline of the different steps that you would take to make a side channel over the L1 cache. In this example, you first have to determine co-residency. So you're trying to create a side channel in the cloud. And you launch your VM, you start running your processes, and you're listening to the environment. You're receiving information about the L1 cache's behavior from your new VM. So you classify these patterns, and you have to have some beforehand knowledge about what that pattern should look like. What's your target environment? And once you can reduce the noise and kind of see a clean signature or environmental signature, then you can determine if you're co-resident or not. So does that map to a pattern that you expect, or a pattern that you know is being created by a specific type of process? All right, so the first demo, I actually didn't have time to run this, but I have code on GitHub later, is over the L3 cache. I guess there's a whole talk about that earlier, so I won't go too much in depth, but for this case, there was a timing attack vulnerability. It's a simple method of recording how far into memory do you have to go to receive your value. And based on that distance, it'll take longer or shorter to receive that value. And using this method, you can determine many different things, but in most cases, and in the code provided, you're stealing the sender or the transmitter's RSA private key. So I have some diagrams here. It's called the flush and reload tech. There is a paper done 3 years ago now, linked to at the bottom. And this was one of the first large papers that showed how powerful the L3 cache is as a side channel medium. So it's very efficient, it's very reliable, and simple in a very elegant way. So what you're doing is the receiver is forcing specific code out of the L3 cache and measuring later after it waits a little bit. And the transmitter is performing some RSA encryption in between that forced eviction and measurement that the receiver is taking. And based on what the transmitter is doing, or the victim is doing with RSA encryption, the receiver knows that, that new value was put into the L3 cache, so it actually took a lot quicker to receive it back, or not. Now, this attack did require knowledge of the target code, so the receiver had to know what sort of code it was looking for before it evicted it and measured access again from the L3 cache. And you can go to these two links here to find more code or a detailed write-up about that attack. But they were actually very successful. So in this example, they were targeting the GNU PG encryption method. All right, so for demo 2, this is the work that I presented at Black Hat last year. And the medium I chose to do for my thesis was actually the CPU pipeline. So I chose this one because it's less used, and it's also a little harder to measure. So like I said before, you can't directly introspect into the CPU to see the state and see it changing over time. You have to, or the pipeline over time. You have to find a clever way of measuring the CPU without changing the instructions that are in that CPU at any given time. So the vulnerability here is actually erroneous return values. So what I do is I have 2 threads, and I can see that after they go through the pipeline, after they're executed, the values I receive back from these threads are incorrect, and I'll go into detail later on. And for the specific attack, which I'll show, I created a covert channel. So one process is sending a message to another. And I say cross VM here, but it's cross VM on, in the cloud. So, all right, so I guess I kind of skipped ahead, but specifically when I'm measuring these erroneous values that are returned from my threads, the reason they are erroneous is that the pipeline actually has a lot of different optimization methods. And when I put in my computation through the pipeline to execute, so do some math in the pipeline, it actually uses a method of optimization called out-of-order execution, which will change the way in which my instructions are executed and change the return value that I receive. So based on that, I can create a receiver which is measuring. So it has these threads, and it's looking for these erroneous return values. And based on the quantity of those values it receives over a certain time frame, it can determine bits of meaning from that. The transmitter, on the other hand, has to be able to deterministically force the pipeline state to either optimize or not. So to either reorder my instructions to return incorrectly or not. And this requires that some sort of prearranged time is set. All right, so I know that I'm trying to force deterministic memory reordering. So I'm trying to, at runtime, force a specific way of reordering my instructions in the pipeline. And I'm doing this on x86, so that means that it's a usually strong memory model. So that means usually if the pipeline is unsure, it will not reorder my instructions. And I can use one of these 4 things down here. So I want to either tell the pipeline to reorder or to not, to optimize or to not. And it's quite handy, but Intel provides us with 4 different types of semantics that we can use as memory fences. And we're going to focus on the store load, which tells the pipeline to not reorder my instructions if there's a store to memory and a load to memory in that order. So to keep those 2 sequentially consistent. So specifically in assembly, this instruction is called the mfence. And it's quite an expensive operation, but it does what I want. And it forces the pipeline to, in a specific time frame of instructions, to maintain the order of my code, to make sure that loads to memory are done before, or stores to memory are done before loads. Now down here I mentioned that this requires simultaneous multi-threading to be turned on. That's not a problem usually, just because that's the default for all modern computers, if not most. But this just means that 2 processes running can share the pipeline at one time. So the pipeline will execute a few instructions from one thread, execute a few from another, and so on. All right. So this is what a diagram of what it looks like in the pipeline. So you have some random instructions, and it's storing and loading from memory to the same spot in memory, so value X in memory. And the mfence is just going to keep those 2 separate. It's going to force the store to happen before the load. All right, and this is the page from the Intel manual detailing how this is possible. So saying that without memory fences, your instructions can be reordered. And they even show this case down here where you have 2 processes, so 2 threads, and they're storing and loading to the same spots in memory, so X, X, Y, and Y. However, the processor doesn't notice that the stores to memory and loads, which even though they're happening to the same spot in memory, are actually happening in 2 different threads. So it treats them as if they're separate spots. And it can actually reorder them such that in this example, R1 and R2 could be 0. So the loads from memory will happen before any store to memory. And this is what it looks like. So as a simple receiving mechanism, I create 2 threads, and I basically use the same code that Intel provided in their example. So if you run this multiple times, you realize that synced happens occasionally. So this is when your 2 threads are running perfectly in time with each other. The stores happen as expected before the loads, and you get R1 and R2 equal 1. In the asynced example, and this is the majority of cases that you see even if you're running threads in Java or different programs, the stores and loads happen at different times, but they don't really get reordered. So you just have one thread moving faster than the other. And you get R1 equals 0 or R2 equals 0 and vice versa. But in the out of order execution case, and this is what was being discussed in the Intel manual, the loads happen before the stores. And this is in the case of no memory fences at all. So the pipeline feels like it can reorder. It's not instructed to memory fence your instructions. And so it reorders these 2 loads to happen first because it doesn't realize that the 2 threads are actually affecting each other in memory. And this is the case when R1 and R2 equals 0. So this out of order execution case is what we're measuring to determine if our instructions got reordered in the pipeline or not. And that's going to be the way in which we can receive information from the pipeline about the state of the pipeline. All right, so just some general information about my setup before I go into it. I used Intel's Core Duo Xeon architecture with 2 cores. I used Xen hypervisors because that is the most common scheduler out there, used like in Amazon Cloud and things like that. And these things I mentioned before, but my 2 processes are running in the same pipeline, and it's a relaxed memory model. All right, so this is a diagram of what my setup is looking like. So I have a few VMs, they're all Windows, and I'm running processes and they're sharing the same core. So they're sharing the same pipeline and running simultaneously. And that means that instructions from one will actually be able to affect the state of the instructions from the other thread. And that's, this is what I did specifically in this example. I only have 2 VMs running and processes in each to either add fences to the pipeline or to receive out-of-order executions from the pipeline. All right, and if you want to read more about this setup or what I did, you go to my website there, you can find all my code as well as a paper I wrote about it. So, right. And this is what happens over time if you measure in different time intervals the number of out-of-order executions received. You actually can get a pretty clear signal that comes across the pipeline. So in this case, out-of-order execution frequencies on the left, I represented a 0 bit as a period in time where there's not a lot of out-of-order execution. So there's lots of fences in the pipeline. There's no memory reordering. And then this bit here is represented by a period of time where I didn't send a lot of fences to the pipeline, and I actually received a lot of out-of-order executions after running my 2 threads thousands of times. All right, so I'm going to show this short video. And this is just my Zen Center setup with my different Windows 7 VMs. And I'm going to go into it. This is my demo from Recon last year. And so for my receiving code, this is the receiver measuring the out-of-order executions from the pipeline. So it's running different threads, and I have it calibrated such that in a given time frame, if it receives, in this case, I flipped it, so a lot of out-of-order executions to represent that as a 0. And you can create a different mapping for different number of out-of-order executions received, but that doesn't matter as much as the fact that you can deterministically change the state of the pipeline as well as measure it. So in this case, I was just showing that I'm canceling the noise out from the system. So all the other processes running, I kind of cancel these data points out. And that just takes a lot of data aggregation and knowing the environment that you're set up on. So that was the receiver. With the code that I provide, I also write it to a text file, and that sort of thing, just for more data analysis. Now my sender is the one sending the memory fences into the pipeline. So that's in a specific time frame, pushing many fence instructions into the pipeline to force that state in the pipeline medium. So to force it to not optimize and not reorder my instructions. And actually, I do have to use a lot of fences, but you can see that my 2 bits got read. All right, so the video ended before I could stop it, but in that scenario, I was just waiting for a signal to then launch an attack. So you kind of saw the end of a blue screen there. But the idea was that it was waiting for a signal and then to launch something. All right. So from this specific side channel, there was a couple benefits when I compared it to side channels over other hardware mediums. So from a hypervisor point of view, it's actually a little easier to see patterns of behavior of processes querying different parts of memory. So using this method of recording the pipeline, it might be a little harder for a hypervisor to detect that anomalous behavior. Another interesting part about this is eavesdropping mutilated the channel. So if I had another process in the cloud or something at the kernel level listening to other processes reading the pipeline or trying to listen for periods of time where there was a lot of instructions of the same type. so maybe of the M-fence, being pushed into the pipeline, eavesdropping would change the noise canceling algorithm. So it would change the state of the pipeline enough where my receiver would not be able to receive the same channel and be able to detect that someone else was listening. And all these other things are specific to this side channel, but it wasn't affected as much by other system noise. So a lot of processes running on the same CPU, like in the cloud or something, that definitely changes the cache more, the other parts of memory more, because there's more processes contending for the same resources. But this channel was interesting in the fact that a lot of other processes running on the system didn't necessarily change the way I read the pipeline. All right, so what are some defenses you can use for side channel attacks in the cloud or against any sort of hardware side channel? So isolating a VM or isolating processes is honestly the most assured way of making sure that your process is protected. But the problem with that is without hyper-threading turned on or without sharing resources, you do lose a lot of optimizations that are provided by the computer or by the cloud. All right, so I've read a lot of papers about hypervisor anomaly detection. So this is when the hypervisor is kind of cued into listening to different resources on the system to see if one process is using it more than others. And this is probably where a lot of larger cloud companies are kind of moving towards, right? So they're trying to build intelligent hypervisors, which look for different patterns in the system to see if they also can kind of eavesdrop on a potential channel being sent or being received. And applying a little machine learning or data aggregation, these systems could become quite powerful. So in the same way that you have networks which predict what should be proper behavior on that network, you could perhaps have a hypervisor which could predict what proper behavior should be seen at the CPU or at the cache level. All right, and there's also defenses you can use at the software level. So let's say you want to deploy your VM or your processes in the cloud, and you know that you maybe can't trust the cloud or trust your other neighbors in the cloud. So what you could do is add noise to your system. So you could add noise to your processes to add different patterns that it uses to interact with the system. And also an interesting one, which is used mostly by cryptographic libraries now, is trying to create everything with constant time loops. So a lot of side channels are built, especially in crypto, are built around the fact that it takes different amounts of time to execute different mathematical instructions for different length bits or different values for variables and things. So constant time loops and constant time algorithms are very powerful, especially in hardware-based side channels. So I kind of talked a little bit about the future already, but I think we're definitely going to see more resource sharing. So there's going to be more and more dynamic optimizations being used to either scale large systems in the cloud or even on your own CPU. So virtualization is going to be very powerful in this field, but again, that leaves large gaps for side channel attacks to take place. Also, malware is an interesting area where this could go into. They have seen malware which uses network packet side channels, for instance, to change its behavior or to determine if it's in a safe or unsafe environment. I better finish fast. But there's a few things to consider. So outside of the realm of side channels, in the cloud itself, hypervisors are still very vulnerable, right? So we saw a lot of great talks the past few days on hypervisors and Zen and things like that. I referenced this one I saw at Infiltrate this year. But hypervisors were kind of in the dark for a long time. They got away with not doing a lot for security. And so until recently, they were pretty vulnerable and open, but no one really looked at them. So those things have to be hardened as well if more of our processes get deployed in the cloud. All right, so in conclusion, I hope what I mentioned today helps you come away with a better understanding of specifically hardware-based side channels, as well as the primitives needed to create them. So build your own side channel kind of thing. What mediums are available in the cloud, so what attack vectors could potentially be vulnerable for your processes in the cloud, or areas of research to look into. And hopefully gave you some ideas of possible attacks or research vectors to go to in the future. So I'd like to acknowledge Jeremy Blackthorne, my research advisor, as well as RPISec and Trail of Bits, where I work. So if there's any questions, I can take them now, or you can reach out to me at any of these links.
Thank you. Any questions? Up here.
How easy do you think it would be to industrialize this sort of thing if you're, some large actor with time and money and you wanted to go after the, SSL keys of, Amazon or someone like this, and to just spin up VMs in the cloud and hope you get lucky? I mean, how easy do you think that is?
There's a paper about that actually. There's one, it's hard to determine co-location in the cloud. That's actually, most of the time, the thing that's protecting vulnerable pieces of software in the cloud is the fact that attackers have a hard time determining co-location, because there's thousands of Amazon boxes. And the most common method of getting around that is just spending tons of money and spinning up all these VMs, taking readings from the system to get a signature of that cache or that environment to see if that's something you're looking for or not. So people have done that, for sure.
Is something like Intel SGX something that you could use to protect against this, or is that this wrong sort of ballpark?
No, I think that would work. The problem is, right now at least, is a lot of these larger providers of cloud services, they do have other problems. They do want to maintain optimization for their customers and things like that. So that would certainly be a great solution for maybe like a personal computer, deterring side channel attacks. One person I know, she does a lot of malware research, and a piece of malware may be looking for a specific environment ID, and you have to have a very specific setup to make sure that your VM actually has the same hardware virtualization that your main operating system does. So that might be applicable in that realm.
Thank you.
Any other questions from the floor? No? All right. Well, thank you very much, Sophia.